morning everybody and welcome to the NPTEL online certification course on semiconductor devices for next generation field effect transistors, physics perspective, and this is lecture 19 and the topic of the lecture is basically SPICE installation setup. So, we will be going through how will you install SPICE on your laptop or a desktop, and we will be looking into installation setup and if possible a usage demonstration using a SPICE tool. So, let us look at the outline. We will first look into setup, then brief idea about the schematic window which we will be using, and then a live demo of a small circuit. So, if you look at the framework of SPICE primarily, then we primarily do what on the left hand side if you see is basically a PMOS gate, right. This is a PMOS gate and we do a schematic entry in the PMOS gate using PMOS gate and some circuit, basically an RC circuit has been shown here, and then we try to run it, we run the net list and then we do circuit calculation. The simulation is performed by the simulator and the simulation results are given to the output deck in the output side. So, the graphical representation of the output is also available to you. You can also have a lookup table approach being developed within the EDA framework as well. So, netlist is basically the textual representation of the simulation information. Say for example, which components are you using, right? Is it an active component or a passive component? What type of analysis will you be doing, a DC analysis, will you be doing an AC analysis, or you will be doing a transient analysis. So, that information is carried by the netlist. And then similarly, if you look very carefully here, we also insert the model files of these NMOS and PMOS, which we have already discussed with you in the previous lecture. And these model files are inbuilt model files within the EDA framework. And when you recall these model files by putting a .model command in the netlist, you will be able to recall those model files from the library. If you look at for example, the first one, we are giving a DC bias of 5 volts here and component name is referred to as V1. So, I have a V1 here. Similarly, we have a C1 whose value is given by 1 nanofarad and we have this resistor whose value is given by 100 ohms, which you can see here, and so on and so forth. And if you look very carefully, we are doing a DC analysis here where we are going my V1, which is what is V1 is my DC bias here, is varying from 0 to 3 volts with a step of 0.1 volt. So, the syntax here is dot DC and then you have V1. V1 is the component name, the starting value of the DC component sweep and the ending value, and then followed by the increment which you want to give. So, this is basically the representation which you give here. If it would have been an AC, we would write as AC signal here, correct. So, depending on the sort of type of simulation you want to do, you can actually adjust this command statement here and you will be able to extract the simulator and the simulation results. These simulation results will be again published in the graphical form in this case, right. So, this is the operational framework of a schematic. Now, if you want to install a SPICE, this is sort of the hyperlink where you can go, and these are all freely available. Anybody can actually download it. It is an open source software and anybody can download it. Analog devices does have LTSpice available, as you can see here for MS Macintosh and for Windows. There are 2 versions available. Windows version is basically a 64-bit version and you will also start to get updates here. So, for example, you can see here data model has been updated till 13th of September 2024. So, there is an updation going on inbuilt within the LTSpice model and this updation files are automatically added to the final downloaded exe file for the LTSpice. Now, this is as I have already told to you, the interface allows you to actually probe schematic and also produce simulation results, right. You will find good tutorials within this setup as well, which will help you to do it, both for power, right, both for RF and typically we look at ADCs and DACs, clock and timing, amplifier and linear. Amplifier and linear is basically linear amplifier operational amplifier and so on and so forth. So, this website is quite useful, and I would request you to go through this website and have a look at the various components. There are certain example files also which will help you to understand the LTSpice in a much better manner. Okay. Let me come to the main schematic window, and once you install on a computer and you click on the LTSpice icon on your laptop, what will happen is that you will open an LT schematic as shown here. So, the main schematic window where you have just like your Windows to ordinary Windows, you have this file, edit, hierarchy, view, simulate, tool, window, etc. And also you have these icons here which you will learn as you move along, right. So, something is that to do with printing, something is to running it, something for debugging purposes, something is copying and pasting and so on and so forth. All these are available as a iconic tool in the schematic window itself, right. This is the basic entry framework for the LTSpice in this case. With this, let me come to the major component sort of location, which means that where the basic components are located. So, within the main window you will see the components are located here. Say for example, this I want to draw a wire, then simply by clicking it I can draw a wire, right. And when a wire crosses another wire, right, it comes in links. If it touches the other wire, it will be a sort of a dot produced, which means that these two are not only intersecting, they are actually electrically shorted also. Similarly, you look at this is basically a ground, and ground is always required, as you know, for any convergence in the circuit simulation. So, this is your ground, this is ground, and then followed by you have here a resistor R1, and once you double click on this resistance or a C1 or L1, you will be allowed to enter the value of the resistance, capacitance and inductance respectively, right. And so, if you want to add a component, click there, drag your mouse onto the schematic, and the diode, inductor, capacitor, resistor will all appear on the schematic itself. Double click on it, and what will happen, its corresponding model files will try to debug what you have done and give you that R1 value is required, C1 value, L1 value, and let us say when you talk of diode, maybe the what value of what silicon or germanium are you taking diode, so on and so forth, they will allow you to do that. Similarly, if you look here, we have this operational amplifier here, U1 is the operational amplifier here. You can also delete, shortcuts are there, you can also delete any of them, right. You can use F5 or Control X, and if you want to move either a wire or any of the components, use F7, right. And if you want to drag it, you can do it F8. So, dragging basically means that the interconnects remains the same, but you want to drag the active devices from one part to another, right. So, the wiring will adjust themselves so that the wiring is still maintained in the same manner as it is there. Whereas, if you want to move it, you want to basically click active device, remove it right from the schematic itself, and you want to add another one. So, to add a component, you need to click that corresponding item as I discussed with you. And of course, as I discussed with you, you will have voltage and current sources, you will have transistors, operational amplifier and other user defined materials will be available to you. And these are all interactive in nature, and you can therefore double click, say for example, on an op amp and discuss, you can define the offset of the op amp. Now, internally what it does is that when you write the resistance value of 100 ohms, it goes back to its model file, make the changes there such that 100 ohm is emulated by that schematic. Same thing happens for capacitor, inductor, diodes and operational amplifiers. So, this is the general major component location in a SPICE model file which you will see. Now, let us come to the usable feature here. Two things which I will show you here is to rotate it, because you need to rotate these active components on the schematic, then use Control R, right. And before placing it, if you want to rotate it, Control R, and if you want to mirror it, then you make Control E. Mirroring is, so it is something like this, that the mirror is attached somewhere in the middle. So, they are diametrically opposite here, and rotating means generally rotation to the right, right. In the clockwise manner, you will start rotating it, and depending upon how you rotate it, active component will behave in that manner. So, rotating or mirroring does not change anything of your model file. So, they still remain the same, right. And as you use more and more EDA LTSpice, you will see that more and more usability will be appearing in front of you. Let us look at the toolbar summary now. We have already discussed these things more often. So, this is a line, this is a ground, right, and this is a label a node means, say let us suppose I have got this, right, and I want to label this node as X, then you just click here and the node labeling will be done. Then this is your resistor, this is your capacitor. Once your node labeling is done, obviously as I discussed with you, this is the resistor, capacitor, inductor, I have diodes, and then for various circuit elements you press here, then you will get various values of the circuit element being introduced here. Let us come to the right hand side, most right hand side. So, I will tell you what we are doing. Actually, if you start from the left hand side, you have standard open save command and you have this simulate command. So, from here to simulate, run, save, these are all sort of left hand side are all reserved for simulation and also for evaluation. On the right hand side, you basically do more amount of editing issues. For example, you want to rotate, you want to mirror, you want to place and comment on it, you want to place a spice directive directly can be done from these right hand side icons here. So, these right hand sides are primarily meant for moving, dragging, undoing and so on and so forth, right. Whereas, left hand side is primarily meant for spice model simulation, zooming in, zooming out and so on and so forth, whereas the middle one are primarily the tools, affective tools of active and passive elements which needs to be dragged and dropped onto the window schematic. So, if you look at this one is basically move, then this is drag, then if you want to undo this, this is the redo, right. You want to rotate it, you can rotate it, you can mirror it, you can doing this, and then you can actually use place comments and you can actually do spice directives also in this case. So, we have learned this as well. Now, let us come to the last one which is on the left hand side here. So, as you can see this is find. So, if you want to find any command or anything within the netlist, right, copy paste, this is copy, this is paste. If you want to delete something you need to delete right there, exactly like the ordinary windows which you have used, and that is the advantage or the beauty of a spice model or specifically the LTSpice which I am showing here. It is very close to the windows. So, anybody handling windows, it is almost like a second home in case of window users. On the left hand side you will see you will have this an icon of man running is basically running the netlist, and this is where you simulate it. You zoom in, you zoom out, and then there is another and you copy paste, zoom out, pan, so on and so forth. So, this is the basic toolbar summary which I wanted to present in front of you in order to appreciate the overall nature of this. Let me come to the basic circuit connection of a spice model file. So, what you do is that you first of all drag and these wires can be then placed, and as you can see as I was discussing with you, this point shows that this wire and this wire are shorted together and it is connected to the ground in this case. So, what you do is that when you right click on these components here, then this sort of box opens. This is the box, right. This is box which tells me how much DC value you should push and how much series resistance you put. Now, please understand, here comes the concept that if you are using a DC bias or any voltage source, the output impedance of a voltage source is almost 0, right. Output impedance for a voltage source is equals to approximately equals to 0, very close to 0. So, the value which you will feed here series resistance should be as small as possible, right. And this again if you do not fill it will take some value in sort of in a default mode and carry forward with it, but if you want to feed a value you can do that. Similarly, if you look at the resistor part here, it tells you what value of resistance do you want to place, right, and that is user dependent quantity. What is the tolerance and what is the power rating? Tolerance basically means that if I give let us say 100 ohms resistor, percentage tolerance primarily means is a 10%, it effectively means that resistance can vary from 110 to 90, right. So, that is what is known as tolerance, and then power rating basically means how much power will it dissipate, right. So, if you remember I square into R is basically the power which dissipates. So, why this power is important? Let us suppose you are doing a high voltage simulation here, or maybe let us say a power electronic simulation here, where the currents are very large, then I square into R is also very large, and therefore, if your output power dissipation is much larger than the maximum rating, power rating of the device or the resistor will actually burn out. So, a priori you are told that you need to define the value of R1 in terms of both its resistances, tolerances and its power rating. 3 important points for resistor and 2 important points for voltage, which you see. When you click advanced here, for example, if you look at the voltage source here, if you click to advance, you will see many other profiles coming up. For example, if you are not using a DC and if you are using an AC source, then what type of low to high transition TR, TF will be, rise time and fall time, what should be the pulse width of my AC signal, and so on and so forth. So, there will be multiple such issues when you come to the advanced part of it. So, this is the basic circuit connection which you do for a SPICE body. The installation can be done, let me show you here, using this one you can do an installation, right. Later on I will also show you maybe a video of one simple SPICE based approach I will show you. But to reach to that level, first of all please install the software either through this or any other package which you have with you, and this will be useful for simulation purposes. Let me come to the diode models, because now we are entering into a region where we should know, because you are circuit engineers and you are device engineers. So, when you plug and play these models from the library of EDA onto the active schematic, you should know what the models mean and what are their values in order to manipulate those according to your own requirement. So, what we will do is that we will take up the basic PN junction and look into its characteristics, right. We will look into the basic diode equation and then example of a diode circuit and then maybe a practice example. Okay. Just to give you an insight, all of you must be aware of this basic idea. So, I have a PN junction diode and it is shown in this manner, right. I have this diode here, this is my P side, right. This straight line is my N side, right. So, I have a P side on the left hand side, on the right hand side, and I apply a bias, a DC bias. Even a DC bias will help me in external understanding it, such that the positive side of the battery is connected to P side and negative is connected to the N side. This is of course known as the forward bias, right. This is forward bias. Now, and if you reverse it, which means that the negative side is connected to P side and the positive is connected to the N side, then we define that to be as a reverse bias. So, this is forward bias which I was talking about. I can also have a reverse bias in this. This is reverse bias. Let me put a resistor for the safety purposes. This is, let us say, diode, this is anode, this is cathode, and a current like flows from this point to this point, right. In fact, the current will be 0 in the first place. Now, let us go one by one and see what happens what happens to those who are not initiated in diode will be able to appreciate this point, that when you have a PN junction, right, when you have a PN junction, then you have P and N. So, even if you do not apply any bias, external bias, because of the doping concentration difference between across the two edges, this is known as the metallurgical junction between P and N. So, what will happen, the electrons from here which are free in nature, they will start shifting towards this side, right, and leaving here what, Na plus, right, and when they reach here they will recombine with holes and therefore, they will be left with Nd minus, which means that after some time when you add these P and N junction through a metallurgical junction, there will be electrons moving by diffusion from N side to P side, thereby leaving positive charges on the. So, this will be Nd plus. So, this will be Nd plus, this will be Na minus. So, this Nd plus will give you the positive donor. The donors have actually donated one electron and becoming a positive charge, and since holes are being donated on the left hand side, it becomes a negative charge, right. So, you get such type of principle, and therefore, even without any external bias, if you want to have a look, there will be something like this, that you will have a p-n junction, you will have a material junction, and if the doping concentration is exactly same on both p side and n side, my depletion width here will be also same as the depletion width on the n side. So, if this is xp and this is xn, provided the doping at Nd equals to Na, on the both sides the doping concentration is the same, then I could explain that Xp equals to Xn. The depletion region is same. Now, if you apply a positive bias, which is I apply a positive bias, basically mean I am applying this, then what you are doing, you are forcing the whole electrons to move in this direction and forcing it to this side. Now, let us see a very interesting point which will happen. Within the depletion region, right, this is P, so this is positive, N, so this is negative, but the reverse will be true within the depletion. So, within the depletion region, the electric field will be directed in this manner. This will be the direction of the electric field. I hope you understand. So, when the electrons actually enter here, right, they tend to be sort of forced out of the depletion region by this electric field. But who allows, therefore, for an electron to move from n side to p side, it has to cross across a voltage barrier or an energy barrier. Who gives this? Because of this electric field. And who helps you to overcome this? This external potential bias, right. So, this external potential bias which you are giving, this V voltage, is trying to overcome this bias here, and it tries to move ahead. Once it does, the depletion region in forward bias therefore reduces and the current increases. That is what has been taught to you in your sort of a device basic course. However, let us look at the fact that if you did have a, if you apply a reverse bias. So, reverse bias will do what? This was your initial p and n side doping concentration or the depletion region. When you apply a reverse bias, what happens? The depletion thickness actually increases, right. So, in the forward bias, the depletion region was smaller. In the reverse bias, the depletion region becomes larger and the current starts to fall down. As I was discussing with you, this is my depletion region, right, and I had this p side, n side. This yellow colored, this region is near the metallurgical junction in my depletion region. This is positive, negative, and this is the n region having large number of electrons, p region having large number of holes. Therefore, in the forward bias, till a time means till a voltage level, you will never find a current, and the reason is that much amount of voltage is not enough to overcome the depletion width voltage, and therefore, the current is almost equals to 0. Around 0.7 for silicon, you will see the depletion barrier width is broken down, and as a result, suddenly the current starts to increase, and this is almost like a exponential rise in the current happening here, right. So, and we define this to be as a knee voltage, this to be as a forward voltage. In the reverse bias case, as I told you, the current is so small, there is almost no current flowing through the device. So, this is of the order of milliamp and this is of the order of nanoamp. So, this is about 6 orders lower on the negative y axis, and therefore, you can see this reverse leakage current, which is because of some reason, I will come to that later on, you will have small current. Reverse leakage current is primarily why? Because in the reverse bias condition, you will have some amount of holes here. These are minority current carriers on the n side, and there will be some electrons here. For them, it is not a hill, it is a basically slope downwards, and as a result, what will happen is that there will be some amount of current, because some electrons from this side can actually go very easily and recombine with the holes here. So, that is the reason, that is the origin of the reverse saturation current, which is again a temperature dependent. For every 10° rise in temperature, you will see almost doubling of the reverse saturation current happening. At certain point of time, which is known as the breakdown voltage, you will see that the current suddenly starts to increase, because there is a breakdown of the depletion region, right. So, we have learned two things from this: forward bias, negative bias, how it works out, and reverse bias. We have already discussed this point, and so in reverse bias, your depletion width is increased. In the forward bias, the depletion width is decreased. Therefore, let us talk of a diode as a capacitor. So, in a reverse bias, since this depletion thickness is large, the capacitance is small, whereas in a forward bias, it is just the reverse, right. And this is way how we look at it in the sense. So, let me close this part of the session, and then we will come to the diode model in the next class, so that I can distinguish between the SPICE model and how SPICE model is related to the basic device physics of the course. Thank you.